Um, so what does this mean? So the L1 distances to F for the two choices. Are not close. Okay. However, the integral of f epsilon minus f squared, right? So this, I'm just expanding f epsilon squared to f epsilon f, completing the square here, and 0 to 1, 1 minus epsilon squared minus 2 times 1 minus epsilon plus 1 plus, right, so this thing just boils down to 1 minus 2 epsilon plus epsilon squared minus 2 plus 2 epsilon plus 1. And this is just 1 to 1 plus 1 over epsilon squared, epsilon cubed squared minus 0 plus 0. So this part is epsilon to the 6 over epsilon squared. And this whole thing just becomes epsilon squared plus epsilon to the 4, which is less than 2 epsilon squared. And this is what our L2 distance from G epsilon minus F is. So what is this? Basically, this inequality is going to do is minimizing the L2 error even with F given picks the wrong density. Okay, from the set F epsilon and G epsilon. So for universal performance guarantees, we simply cannot use L2 or maximum likelihood. And so one big criticism of this is that this is all pathological and constructive. But yes, we are in the pathological situation of going after universal performance guarantees, right? So nothing really pathological about these counterexamples. Constructive. So what is minimum distance estimation? Where does this come from? And the folklore is there's someone even more out there than Luke. And I haven't met this guy, supposedly Greek.
Supposedly Greek.
Oh, I think so. His name is Yatrikos. So the whole theory kind of is tango or jazz between Yatrikos and Vapnik-Chervonenkis. And Luke and his gang basically do this. Okay, so we'll get there. So let me start with minimum distance estimation. So let's consider, so back to MBE. So consider a simple problem or a simpler problem of choosing between two densities. So it's exactly the same. Two densities. And Fn and Gn. So they can possibly use the information in the data. So So we want to construct some estimate Pn such that the L1 distance between Pn and the unknown f is roughly or is close to the minimum of these two. And so that's basically the idea behind minimum distance estimation. So to kind of justify this statistically, what are the main ideas? So we use empirical measure. So what is this? It's defined as mu sub n of subset A. It's nothing but the relative frequency of the points, the endpoints that land in A. Right? It's the indicative function of the ith point falling in A. So this number of data points. A divided by n. So in addition to this, we're going to use this next idea called the Cepheid set of the ordered pair Fn-Gn. So the Cepheid set of Fn-Gn is A, and A is actually really A of Fn, Gn. And what is this? It's simply the set of all x where Fn of x is greater than, strictly greater than Gn of x.
Right. Do you want to think about blackboards instead is now next the previous blackboard is yeah.
Oh, it's too far below?
Yes.
So should I put this up?
Yes.
Oh, I see, yeah. Okay, because then you can see what I put.
Yes.
Thanks. Yeah. Yeah.
Thanks.
Yeah, you know, I've been teaching too much computer stuff, so I kind of forgot about
the basic mechanics of blackboards.
Yeah, well, not really mechanics, but you know, the order.
Yeah, but the actual mechanics of it.
What is good? I'm feeling really good right now. This is no computers. So, okay, how do we take an empirical measure in a Cepheid set and produce this minimum distance estimate of a pair of densities to choose from? That's called a Cepheid estimate. So first we observe the following. If the integral of Fn and the integral of Gn are normalized, then we know by Cepheid identity the following. The integral of absolute value of Fn minus Gn is equal to 2 times. So we basically look at where Fn is greater than Gn and do Fn minus Gn all the other way. Okay, so and this is simply 2 times the integral over A of Fn minus 2 times the integral over A of Gn. Okay. So from this observation, we get the Chervonenkis estimate. So the Chervonenkis estimate is Fn star, and it will be Fn if the absolute value over A of Fn minus the empirical measure over A, if this absolute value is less than the absolute value of the integral over A for the second choice Gn minus the empirical measure over A. Okay. And it's Gn otherwise. So I'm going to draw a picture. Maybe it's too elementary for you guys, but I found this first time I looked at it very difficult to really digest. So the picture really helps. So let's just make a simple situation. So because that's the key to everything we're doing, we're going to just generalize that picture. So let's say we have an F like this. That's sort of something like this. And let's say we have a G that's kind of, spiky like that maybe, and something like this. Okay. So this is my Gn, and this is my Fn, and I have observations now. So let's say I have, something like, let's see, this is where Fn is greater than Gn, so let's say I have 1, 2, 3, 4, 5, 7 observations that fell here, and say 2 fell here. Okay. So then basically given my data, the way I sort of it will work is mu sub n of A, right, this is my A now. So mu sub n of A is going to be, let's say, 8 over 10, or 8 here, 8 over 10, and the integral over A of Fn, my estimate, first choice. Let's say this happens to be 7 over 10, as it looks more bulky there. And let's say my Gn integral over A of Gn is 4 over 10. Okay. So then for this sort of choice, my Chervonenkis estimate will be this Fn. Okay. But for a different choice of data, it could be different. So I am actually looking at the area under this curve, and then the area under this Gn curve over the piece A, right? And comparing that to the empirical measure. And so it makes sense that we want this to be small for choosing that. Okay, this is pretty much the starting point. Then we will, so instead of proving this Chervonenkis estimate, let's prove the general case, because if I do this, it will take a lot longer to get to the general one. Okay, so here's the first theorem, or second theorem, or whatever. So this is, now we're already jumping to chapter 6 in Luke's book. This is theorem 6.1 in De Broglie and Lugosi. And the rest of the chapters are like some basic inequalities and things like this, which we will cover in detail as we prove the stuff we need. So this is a theorem. So this is De Broglie and Lugosi. This is theorem 6.1. So let F sub n and G sub n be two densities. Be two density estimates with integral of fn equaling integral of gn.
Just mean two densities. Do you actually mean two density
Two
estimates?
density estimates, or two things we're going to choose from.
Okay.
They can be constructed from the data.
But there's some, okay. So they could be random variables.
Yeah. So they are, and so this is just property of this Chervonenkis estimate we just defined. So the Chervonenkis estimate Fn star, which chooses the best of the two, right? We have following the integral of Fn minus Fn star minus F. So the Chervonenkis estimate minus the truth in L1 is less than or equal to the constant 3 times the minimum of Fn minus F and Gn minus F. Okay, so it'll be within 3 of the minimum L1 distance of the two guys to F, and within 4 times the maximum over, I'll define the script A steps in a minute, a maximum of the integral of F minus the empirical measure over A. Okay. So what is script A? This is the set of all x where Fn is greater than Gn, and the set of all x where Gn is greater than Fn. Okay, so this is the set of all x. So this is just the two Chervonenkis sets, right? For the ordered pair Fn and Gn. So this is the general result, and it looks very, very weak, right? It's saying 3 times the best one. Just want just 2 here, and
Sorry, I didn't
4.
get what is script A, what does the first X mean?
Oh, sorry. So yeah, I'm just being sloppy here. So this is simply the set of all. Remember, it's just the two Chervonenkis. The set of all x such that Fn of x is greater than Gn of x. I'm just being sloppy in this thing. It's the two Chervonenkis sets.
And why is this specify the density estimates integrate to 1? Is the
Well, if they don't integrate to 1, there are other inequalities we can use. If they integrate to 1, then we can basically get tighter results.
I mean, you could have density estimates that aren't necessarily normalized for whatever reason.
Yeah.
okay?
That's quite common in simulation, for example.
Yeah.
You don't need that, right? So you can have constructions that will produce unnormalized ones. And there are inequalities in the book all over tracking those guys.
Out of curiosity, we assume that they are non-negative?
Yeah.
Yeah.
Sorry, this is a bit...
I mean, this is just a technical detail. Just curious.
Yeah. So I don't know, maybe it's because some computer science, I don't know. So you can have unnormalized density estimate, but I think always density estimates will be non-negative because the definition of density estimate told you it has to be giving you the probability and integrate it, right? Yeah.
So I just maybe we'll get to this, but just out of curiosity, you could pick. I mean, we could define. This is basically we're taking a projection by looking at which one of the density estimates assigns a closer probability to a particular set.
Yeah.
And you could do this for any measurable set. So I guess the Chervonenkis set has some special property.
Yeah, I mean, so I think the Chervonenkis set is basically our way in. So I'm about to define the minimum distance estimate, I think, right now.
Okay, no worries.
Yes, I'm going to define the minimum distance estimate, and then we will prove a more general result than this. Because instead of choosing 2, again, because I want constructive solutions, I will be interested in choosing k. From k density estimates, I want to choose the right one, and that's the theorem we're going to jump to next. And that already proof of that is general version of this because here case too. So let me do this. Oh my goodness, it's already 10. So I gave like some other version of these lectures that we call Polytechnique to these French math PhD students. And that's kind of where I got into this 90-minute lecture routine. They all just sit there all 90 minutes. It's like there's no toilet break, nothing. I don't know. So I guess it's maybe a Napoleonic tradition. So yeah, here's the basic problem. So let's note this. Fn star, check the estimate. So what does this theorem really say? It says that it has an error that is within, we're going to just define this to be En, error for n points, 4 times the supremum of A in A f minus mu n of A. So it has an error that is within En of 3 times the best possible error among the 2 choices, Fn and Gn. So it's really explicit, you know. It's so the beauty is F could be one of the 2 things, Gn or Fn, or F could be outside. It could be anywhere in L1. So let's consider this problem. Of selecting K densities. So this is our main problem basically for today. So we have Fni, and that's our notation. Fni where I ranges between 1 and k, and each Fni we will assume it integrates to 1 for all values. Then let Aij denote the Chervonenkis set. So it's really A of Fni and Fnj. And what is this? This is simply the set of all x, where Fni of x is strictly greater than Fnj of x. Okay. So that's our Chervonenkis set for the pair ij. Now what we want to define is the so-called Vapnik-Chervonenkis class. Of such sufficiency. So here is my Vapnik-Chervonenkis class script A, which is simply the set of all A, ij, and ajis such that I is less than j. So we just throw them all together, and that gives us the Chervonenkis sets. Okay, so Yeah, I think the outcast is alive. I don't know. To meet him. Okay, so now we define our chi, the minimum distance estimate. And the E is going to be psi sub n is d f and I of smallest index that, so indices are just running for integers from 1 to k, such that that minimizes the delta I. So what is delta I? Delta I is simply the supremum over my outcast class of the absolute value of any f n I minus mu n. So just I'll use this. So f n I star is my MDE. So this is the special guy. What is I star? I star is the index, the smallest index. So I want the minimum of the set arguments. Okay. So that is my minimum distance estimate. And so the key object we really need to hunt is every element of the outcast class. Right? So there is actually, formally there will be k square minus k such sets, right? And they can be very complicated, possibly. Okay. So let's continue. So theorem 2 is about, oh, thanks. Today's coffee is provided by SEB, by the way. So I thought it would be nice and touching to do the most theoretical one for us. They've been quite good, I should say. Because they pay your salary for the whole day, right? I mean, it's 5 or 6 people for several days, so it's good. Okay, so let me write down the theorem and stare at it, and then maybe we'll take a peek of it. So this is our theorem 2. So it's about universal performance bounds cover something in the so this is essentially de Broglie-Lagousse's chapter 3 theorem 6.3. When we are setting up from a finite set of quantities. So what does the theorem say for the minimum distance estimate? Psi sub n. We have for each n, so no matter what n is, however large but finite, the integral of psi n minus f the L1 distance to the unknown is within 3 times the best possible thing in your collection of k things, right? Plus another 4 multiplied by delta. And what is delta? Delta itself is the same thing. Supremum of k over the cost class, just as all the Strecker sets of f minus mu n. That is basically should we continue for 5 minutes and have fika, or should we have fika and then do the proof after the fika?
Can you do 5 minutes? Can you do the proof in 5 minutes?
No, at all. I can, really,
But we don't want to. We don't want to.
Yeah, I think I won't understand it if I do it in 5 minutes myself, because I forget everything. I really understand, so I won't keep it. So
Let's take a break.
yeah, let's maybe take a break. It's not too complicated. It's just some mechanics, actually. This one, but
Once one starts questioning whether or not to have a break, it's probably best to just take the break. So.
yeah, we can just do a start 5 minutes early. So we'll do a 30-minute break. And then,
Oh, 30 minutes.
When we resume? When do we start again?
we'll start like 5 to 11:30. Or sorry, 5 to 10:30.
25.
10:25. I'm trying to do the Swedish time thing. It's not working.
This is true. This is funny. I never thought of this. 5,5. Yeah. You say 5 to 1. This is slightly weird. Pardon? Okay. You want to get some coffee? No, we have
Probably message some students to come for coffee if they want. Because we have like, I think I ordered for 20 people.
See if anybody is upstairs.
Yeah, if people want, there's also some pizza. Yeah, we're just getting warmed up.
Yeah.
I mean, I'm not sure. I don't think it will be very easy for some driving cars.
No, but I like it. I like
Yeah, I mean,
yeah, it's really.
it's a philosophical thing.
How can we guarantee how much
Because what will go wrong is ideas anyway. It's not the real world. But the nice thing is.
But these should be fairly robust, I feel like. These minimum density estimates.
No, this is the only theory I'm aware of where.
minimum distance?
Yeah, sorry. Minimum distance. I feel
Where there's no compromise at all.
So to what extent you can show optimality of?
So just a quick comment. I mean, if you deviate from IID, there's mostly just, I mean, the main key here is just that the empirical measure converges in a sensible way.
You can do some Markov things and.
Yeah, I mean, this in general, if you have anything where you have any chance of doing anything sensible anyway, the empirical measure.
What I meant is that the mathematical model itself could be wrong.
Yeah.
I mean, whatever it is.
But it should be fairly resistant
To the model, yeah. I mean, this is, I hope, like, Thilo gets all pumped up about this and
Actually,
gets into the scalable version of this, because we do this tree matrix arithmetic. So if I have time, I'll get into what Gloria and I did. But that's all single machine, right? So if you can push.
I might actually need something like this for a proof. Do you know if you have some holder or something? If you
make some other assumptions. I mean,
make some smoothness assumptions on the class, can you?
Yeah, so there is I'll briefly make this connection in a few more pages, because you can take these k points to be what are called scalable points in some smoothness class, and then whatever this n sub epsilon becomes Kolmogorov complexity. So you can start playing with this distance, the first one.
You do some.
How far, the best thing is to the truth. That you can play with that part. But
you
even
need
if
to be
you
connected to some sort of metric entropy of the Gaussian function. What's
Yeah.
the packing number?
So that's I think I have worked with packing number, whatever. Yeah, it's another chapter in Luke's book. But the nice thing is this inequality holds no matter what. Even if your set of k densities are horrible, it will still tell you the truth, right? Which I think is kind of nice.
I mean, if your set of densities is horrible, then this might become quite horrible as well.
Yeah, that's a different problem, right? But yeah, of course, that's a separate one. But this will already probably kill you because this is they're both. But nothing is.
But this should be quite fine then.
Well, what if like f is so far away and you just have.
Yeah, but I mean, then you're screwed anyway.
Yeah. That's what
then you have no chance of doing anything in the end, anyhow. So.
Anyway, we'll see this. So, are you able to follow?
Not everything. So, yeah, I think I understand the problem.
Yeah.
But yeah, it will take me some time to follow it.
It also takes me a long time to follow, given though I wrote it.
Yeah, these things are conceptually big.
Yeah.
Yes, kind of.
Also, before I started coding, I really didn't appreciate these theorems, like the factual examples and these trees. So the whole idea of doing the support carving is because of fighting that first term, with finite inequalities. Both of them.
So later you change our elements into the tree space.
Well, I don't know. I have this ambitious plan. I was going to get you guys to install this Docker container and play with this tree arithmetic and stuff. But I really want to get through those 22 pages. Otherwise, you won't know the basic.
Right? Do you know anyone who uses them?
Yes. Yeah, I think in general they're not quite exactly in this form, but you take, rather than looking at these traffic sets, you minimize some, you estimate some relative entropy of them. Some sort of divergence measure between the empirical and some reference.
Yeah.
And then you
I think the computer science machine learning guys call this the Oracle inequality, right?
well, these types of things in general are found Oracle inequality. If you read anything about lasso estimates, they'll just speak about Oracle inequalities all day long. But this is a much nicer inequality than the type of thing you get from these lasso and regularized estimates.
I mean, this. So if Luke was here, you should ask him when he comes here. Yeah, it's fun. Are you going to that? Could be interesting for you.
I'm in the wrong country.
No.
Oh, you're going to be in right.
I will be in Estonia.
What?
This is the randomized algorithms analysis of algorithms.
The same week as more stuff, which is the week before Vilnius.
Okay. Yeah, I'm. Oh.
Anyway, it probably is not that relevant.
Is it? Yeah.
It's here. There's a conference here on the probabilistic analysis algorithm.
show that. Yeah, I think.
But Luke will be in Vilnius, but
Yeah.
he's giving like 3 talks or something.
And Deborah as well.
Yeah, but Luke is right.
Yes, yes.
I don't think Lugosi is that.
No, this is from Barcelona.
I think we need to run some excellent, yeah.
Because I can know, in my head it just always becomes Bela Lugosi when I read. Oh, yeah. The Royal Lugosi. So it's just always Frankenstein.
In econometrics, we have the same thing, the minimum distance estimator. Is that the same concept here, basically? Are you aware of it?
No, minimum one.
Minimum distance estimator in econometrics.
Oh.
It's, I hardly remember it myself, but just curious about the name.
I mean, the question is what is the distance, right? So
Yeah,
it's-
exactly.
Here it's L1 distance.
So if you just define your distance, you just want to minimize it. That's the basic concept.
Yeah.
So then it's
But these guys' whole point is that the only distance you should consider is L1 distance.
exactly. Yeah. No, I guess
They're a bit.
Yeah, but this is not the L1 minimum distance estimator, right? This is a minimum distance estimator which gives L1 guarantees. You could try to sort of take, if you have an estimator, you could look at the L1 distance between the empirical measure and this. This wouldn't make any sense because, I mean, if you have a density, it will always be one.
Everything is
okay.
L1.
Okay, I got it.
Because the empirical measure will always be discrete. So if you have a continuous measure, then you...
Yeah. And so L1 is just saying, I mean, L2 is to the power of 2, right? And L1 is just to the power of 1. It's
absolute value, yeah.
Yeah, absolute value. So it's, I think I got it.
But the problem is here, if you can't say that you try to pick from your reference, from your densities that you're picking between, such that this is as close as possible to the one you pick in L1 distance.
And I didn't really follow the mu there. What is that? Is that the
empirical? So this is just...
Oh, the empirical. Okay, got it.
This is just your sample, basically.
Yeah.
But you encode it as a measure.
Yeah.
Rather than...
Okay, got it. So it's the empirical density function, or
well, you don't have a density, right? Because it just... I mean, it just...
Yeah.
It just looks like this. Right?
Yeah, it's like these spikes.
The measure just looks like this.
Okay.
But it's basically a counting measure.
Yes, it is. I mean, it's a random discrete measure. So this is
What's the name of it? What do you call that measure?
It's called the empirical measure, mu7.
The empirical measure, okay.
of the sample.
Of the sample, yeah, it's a function of n.
Exactly. It's a function of x1, x2, x3, etc. So basically, it's just this vector x1 to xn, but you forget the order in which you got them.
Okay.
Right? Because if you just think of them as a measure, you just remember where each point was not in which order.
Yeah.
But you can't take the L. It doesn't make any sense to look at the L1 or L2 distance between such a thing and our densities, because the densities are actual smooth functions. This would be, if you want to think of this as having a density, then you would have to say that each of these spikes is sort of infinity time.
Yeah.
Because if you try to integrate this, you have a jump.
Yeah.
Each of these points.
So we do that separately, so we integrate the estimate or maybe set A.
Yeah.
And then we just put the.
But it's because you just look at one set. Because then you can compare the number of points, the proportion of points in the set relative to the proportion of area with an element.
Yeah.
But that is sort of in addition to L1. I mean, L1 just means the absolute value. That's the basic.
Yeah, I mean L1 is taking the integral. So I mean the L1 distance. So let's see. It's just this. Make it more explicit.
Yeah, between two functions.
Exactly.
L1 between two functions.
Exactly. So then if you say L1 distance between two probability distributions that have densities is the L1 distance between the densities. But this is what we said before, then that it's easier to think of this as the total variation. I think he called this. Did he mention total variation? So I mean,
Yeah, it's something in the, yeah, I think so, in the beginning.
yeah. So I mean, if F is P and G is the Q, so just these are measures, and then if these are the densities of these measures, then this is, for example, I can never remember what this is the same as looking at the biggest difference
for services
in probabilities
for some expenses. Yeah, for regular finds out. So mainly, I mean,
And that's just because you want to have the most general, we take the maximum, and you want to have the small
research groups as we do.
I mean, this doesn't rely on densities. It's also interesting. You can take any, if you have any probability measures, you can always look at
Freshen up my.
you just look at all probabilities. You look at the difference in the probabilities that the two measures are assigned to.
Even though I don't know that. I mean, we usually use the stuff that's in the Yeah.
And this is just, I mean, the reason this
this is like very.
it's just the argument he did for the 1, 2, 3, 4.
Probably will still be good because we will go for inequality.
But this, even if one of them doesn't have a density, like say, maybe Q is equal to this random,
but it's far from.
then this still makes sense.
Because density.
The thing is, it will just be equal to 1, because you can just take the event
classification as an
that's given by exactly these points. Then this will be probability 1. Because by definition, we've constructed it by putting equal weight values. But it will be 0 here because this is the consideration.
No, well, I have.
Probably
one of the few guys that really want to really push this into the constructive setting. So actually,
probability of 1 point in a continuum is 0.
Exactly. So for if you have a finite number of points, it's also 0. Right. So that's why, I mean, sort of intuitively, one might want to say something in the FM such that the L1 distance between, that's the sort of variation distance between UN and this FM is so small as possible. But this will just always be equal to 1 because this is discrete. So I mean, one can think of this as slightly like an approximation, rather taking the supremum of all sets. You just look at one particular set and then try to pick one clever set. That's a sort of representative.
Sensors are.
But is there any trade-off if you minimize supremum? I mean, there are a lot of other points that you can pretty optimal. But that's what it's trying to show here. If you minimize the maximum distance, I mean, in the measure,
That's like a concrete.
Well, won't you have a problem? I mean, say you have 1 point being off, say how in your empirics, which is really say a wrong will this crash that because you want to minimize?
Well, it depends, right? You can also use it in your financial.
The thing is, to your empirical, or to the distance.
Because of
I think so. Yeah, but the thing is, I think so. Yeah, one thing with the total variations, with the thing you said with the when you discuss these properties of total variation, is that I mean an outlier in general is an outlier with respect to the distance of the slit in space. Right? And I mean total variation. This doesn't sense the metrics, right? It doesn't see distance between points. It just looks at the probability of the numbers. So then if you accidentally add something which is very far away, then this will, I mean, it will But you will only have it
Yeah, so
to
that's
the
one of the main plans.
depending on how large a proportion
We,
of the points
so
are
So if they are rare, you are fine.
Exactly. It doesn't matter. They could be instantly far away, and they would still get a very small effect.
Yeah.
If you can get some spectrum,
Because I mean that is we're sort of simple models, but we have the contact or median regression. It's an L1 regression, and the normal regression is an L2. You can see that. And then L2 has the problem with
Exactly. But there the difference is that the L1 is L1 on the space of points.
yes, exactly.
While this is L1 on the space of the probability. Which is an easy, I mean, this is very quickly gets confusing when you have probability on spaces, and you have this distance between probability and this distance over the sort of underlying point. And there is a lot of theory regarding how to relate these two which case you can relate.
They don't account
so he's sort of working here in the space of probability rather than
Exactly. So thus far, there's very little. I mean, this.
Yeah, exactly.
I think in general,
frequently spectrum analysis.
there is nothing here that sort of specifically to this space being Wikipedia
fixes that.
So you take linkage into.
So it's okay. So it's
no, it's weird. We basically
have your density. Then you have your, I guess, your the difference between the points. Or say on your x axis, and then you have the probability mass or function floating above. And we are now trying to make two densities, as close as possible to each other.
Smaller space than pure label trees. And so we have these particle systems we grow on each locus.
So in this theory,
and those particle systems are sitting there.
Set of
And then we can
get densities you can choose from.
a likelihood. So the way we infer
because I think it's
given
I think this is a consequence with nothing else because there's nothing. I mean,
we can.
I guess you have to make sense of this, right?
So we generalize the classical Kleeman coalescent to this way.
Straight into, I don't know if they are random. I'm not sure.
So when this beta parameter is 0, it's the Kleeman coalescent that reshapes topologies. But if beta is
because I mean the first part. I mean if this holds point, you could just apply this theorem to every real. So if you have a random distribution of beta space, and then could you just apply this shapes this inequality to every real.
So somehow we can capture the tree shape at the branches in the semi-parametric way. So we don't really. So what this means is there will be equivalence class of histories that are compatible.
But then you'll want the tree
locally.
Do you know if we get that far, so we get sort of an estimator for a density given the sample estimate arriving at reaching them, or I mean to estimate it, do we get this sort of boil down to okay, this is the way you suggest.
For example, sleep should really.
So I think what will happen. So but I think the idea will be to pick these alternatives, these FNIs. As
so it's
sample
easy
class
for
example, different.
So you have to grow these
for different values that are positioned these different ways. Something. And then you take sort of a good each is what you need with this idea. So that it gives you a way to pick histograms by adapt it.
You'll never produce a sequence.
And hopefully we'll get there.
But I don't know what I'm zero.
I mean, that would be convenient, obviously.
For example, if you see
yes, you could probably do this in
7 and 8 and on the sample of 15.
So this is more general orientation about floating above the
usual way of
exactly. So I mean, it could be that you know something a lot. For some points, that you know a lot about the structure of the density.
Yeah, so
I think the first thing we can do is just these FNIs.
Well, no, I mean,
basically, if you
read the paper, right?
very handwave, you know, but if you have your space on multiple, so this is our space of probability distribution.
So there is some notion of what is
this, and then you sort of just pick a set that sits nicely within this. So you pick sort of representative points from everywhere, and then you take a finer mesh as you go bigger and bigger, and then you just pick this sort of.
All we do extra is we have a local genealogical
So the point is you do it in such a speed that this then becomes smaller and smaller, because you take sort of finer sets, so that you can come closer and closer to the real one. This one will become bigger and bigger in general, because it becomes larger and larger. Because if you take more and more sets, then this class will become more and more complicated. So then you need to do this balancing act, so that you make this finer, quickly enough for this to become small, but not so quickly that this frees up.
Okay, and that is the balancing.
Actually, we corrected for
and that is the balancing. I mean, the optimum to right.
Yes, exactly. We want to find out the tickets and such. I mean, if there's a complex, then I mean, this should this converts for every age separately.
So this is
this is just the lower class numbers. Yeah, I mean, this would be the lower class numbers is just the last 0.16. I mean, unless we refine it in some way.
The C++ library.
So the question is how these different things.
Most people.
All these convert separately, but if you take larger and larger sets, you might include more and more extreme cases, so things that convert more and more slowly. So you need to pick this thing so that these very slowly converting things just arrive as you take n very big to compensate. So you have sort of three moving parts. So we have this moving part. This becomes smaller and smaller, this becomes finer, this becomes more and more complex, bigger class functions, and all of these convert separately, so you need to be careful to be converting seriously.
And sorry, the small a here, what was that again? So that is
small a,
or small a, non-a spread.
This is.
Yeah.
I mean, this is so.
Is that your investigation or?
So I mean, this is a search for a I mean, really,
so this is
sort of the total variation. If this were just all sets, then this would be
this explains a lot.
And the total variation distance between the unknown density and the empirical distribution of the unknown density. But this is what we said, that this makes no sense to look at the total variation because it's not just discrete and this is the point is then that you replace all functions by, in this class, some smaller set. You replace all sets by some smaller class of sets.
This is one.
Because if you just take some smaller class of sets, say that rather than looking at all sets, you just look at the difference for the small intervals. Then this is, I mean,
then we can compare them.
Exactly, because then as long as you have many points in most intervals, then this is this is a bit like comparing cumulative. It's a bit like smoothing, basically. Right?
Or histogram, making them histogram.
Exactly, yes, exactly. But with the running.
Finding the right resolution.
And that's so sort of making all the distribution functions to a histogram. Is that the A script or A? Is that the subset of A?
So I mean, looking at this, what makes this a bit like looking at the total variation distance in a histogram is the fact that this is a smaller class of functions. So rather than comparing on all functions, you're just You're just comparing on certain project sets.
Yes, that fulfills the histogramming.
Exactly. So hopefully, but I mean, if you pick this set of functions here very big, then this class will be very big. Because remember, so this class is the set where one density dominates, all sets where one density dominates another density. So I mean, to make this not too big, which means that this is more like comparing densities, means that you can't pick too many things here. So this is basically the balancing that you.
That is a problem. Yeah, no, it's starting to. I mean, so it will take some time to live through it thoroughly. Thanks.
So it feels like typically you start with a set that you choose.
So my part will be very
fast. Like if your set of functions will be histograms, then you sort of naively you think
that is already
this is
ready.
an
The other thing is just
you seem to believe many histograms. then you restrict
What we need
it
is
to the
input,
final
is
set.
it basically all
Because you have
sites,
some
all
hyperparameters.
genotypes for
Which
all
is the-
sites for all individuals.
Yeah,
Yeah,
kind of, yeah, right? Because you
Well,
want the site
yeah,
data is
Lattice
how
or
we
yeah.
we're going to go for binary instance matrix to the
But you would still need to know, like you said, to know in the surrounding of the sites, that's segregating. You want to know how many observations
feels
you have. If you have an
Hard to
observation,
resolve this to three
Yeah,
things.
I don't know. Yeah, he was telling me there's all this.
That's I mean that's just an artifact of the experiment, right?
I mean, if you take some, if you take, say,
I mean, yeah, I don't know. To have to sit
Say-
down and think about.
I mean, just if one compares to what one sometimes does, at least in sort of regression,
But I guess
regression, if these
So, yeah,
are,
I'm-
if you take these roughly like some wavelengths
for me,
or
it's
something like
I'm
this.
just looking at.
So, I mean, if you,
Okay.
I mean, wavelets would make so much sense in this case, but just heuristically, for wavelets. So wavelets,
What I mean,
like
I'd be
something
curious to see what
at combinations of wavelets that look like
these signals because
this, right?
we
And then,
show these little simulations and arguments that if there is actually a selective sweep, we will see signals.
And in these types of cases, then sort of where one thing is bigger
Somehow
than
takes care
another,
of
or smaller than another, these are just
Yeah,
variables, so you get finer, we get finer.
Where we don't have to hunt for.
So if you can find sort of classes of
This
size
migration
that have
happen,
some sort of structure,
Yeah,
all
it's
the
sort of
crazy
repeating,
stuff we
sort of
don't
recursive
get.
structure,
We
then
just say
the
end of the day,
this is probably
geology
quite
has.
Yeah.
The only not then in the parametric case.
And you have
I
to
mean,
explain
if you want to
what's
keep the
locally
infinite parameter space,
because that's the problem also. I think
would
you
that
have
sort
so
of
many
restrict it to finite?
Okay, you test so many
If you
models,
find that.
and you find the best one, but it
Yeah,
doesn't necessarily
and
have to be
then
great.
Yeah, so this is a semi-parametric approach.
in general, I mean, this is just
Go around it
heuristic.
somehow.
Yeah, but I mean, you can, if you take it finer and finer,
Yeah.
I mean, you can always, so
Yeah.
wavelets, for example, is R based.
Yeah, no, then you can build anything.
Yes, yeah. And then maybe if you take linear combinations, it will, these sets will become slightly nastier, but they're not too much nastier. So it's still something you can find within.
Yeah.
Alright, maybe we should start.
Sure. I can get rid of my doodlings.
So we also live stream the tweet, right? It didn't stop it.
No, this is true.
Are you streaming in the break?
Yes.
Oh, alright.
Doesn't matter.
Yeah.
They get a bit of the break. They lost a bit during the beginning of the lecture when the internet connection went down, so they get a bit of the break instead.
Okay, so let's prove this. So let's cyan be f and I. And let f and j be R and then L minus f. Okay. And let's assume J is not I. Then we have this quality or inequality, the integral, the one distance between cyan and f. Is the L1 distance between f and I and f. That's what we call that, cyan. And then this is just by triangle inequality plus triangle inequality of L1. So we're going to call this star.
guess I should look here.
Okay, so now so assuming without loss of generality that I is less than j, we have the integral of f and I minus f and j. The one distance between the two is 2 times the supremum of a in aij aji f and I over a integral of f and j. So this is just by our surface identity, right? So it will equal to 2 and 1. And this is simply less than equal to 2 times the supremum of a and a over f and I over a f and j. Okay. This is because aij and aji are big subsets of. Okay. And this is less than or equal to 2 times the supremum f and I of a minus mu n of a. Just introduce new n's. Okay. So this is simply a psi n, because that's what the f and I is just psi n for us, and minus mu n of a. And this thing is our delta I, and then we just leave this guy alone. And that's just my delta 2. Right? Because psi n is f and I best function. And so note that delta I is less than or equal to delta j. So because of this, we have another inequality. We can force everything into one of them. So that's just less than or equal to 4 times the supremum over a of the integral of a f n j minus mu n of a. Okay.
This is just delta j, right?
Huh?
This is just delta, right? Delta J.
Yeah.
Yeah, good.
Yeah. Yeah. So then I have mj minus f over a plus 4 times so this is my delta. Just reintroducing x now. Okay, I looks like not convinced.
No, I'm just thinking how did you get that 3 instead of 4? You have 4
Exactly.
and 3 in the theorem.
Well, I'm just 2 plus 2, right?
No.
Oh.
He's curious
Oh,
how
okay.
you'll get to the 3.
Oh, okay. Well, okay. Well, yeah. Guys, equations. So, okay, we'll get there in very soon. So here, let's. So this is just 4 times square p, and okay. So that's and this is because A is a subset of D by D. So finally, this is just 2 times the integral of f and j minus f plus 4 delta. Okay, that's just total variation, so on. So this equality we're going to call star star. So now finally star and combining this with star star gives us the integral of one distance between the minimum distance estimate and the density is now 3 times f and j, so it's 3 plus 4 delta, which is just 3 times the minimum I plus 4 delta. Okay. So we just combine the two and oh, sorry. Oh, it's good. Okay. So what does this tell us? So that's to obtain error bounds for the minimum distance estimate. we need bounds on the delta, the supremal deviation of the true measure from the empirical measure over the Yarkos class. And this is no matter what f in L1 is generating the data. So yeah, this is mu of a, and then there's this integral of f over a. So, and we are interested in delta. So we're going to define this as a function g, the maximal deviation of mu n on mu over the Yarkos class A as the following function g. So delta, and so we make the dependence on the data explicit.
Now we're basically in empirical process theory.
Yeah. Empirical process theory. Yeah, exactly where we want to be. Okay, so what is our plan? So we will first show using concentration inequalities that the probability of this G at being far away from its expectation by epsilon is sharply bounded. Okay. Why do we want to do this? So the maximal deviation, if we can show this, then we know that the maximal deviation is sharply concentrated sharply concentrated around its mean. So then we can just study the mean. And then show using uniform deviation inequality. After we use the concentration, then we can use the that this mean, what does this mean? This is just the expectation of G, which is just the expectation of delta. Can be bounded using the combinatorial geometric characteristics of A. So that part is called VC theory. And for us, we are really just doing daily VC theory later, you'll see why. But that's the general plan for MDE, even beyond the tree-based things I'm interested in. Okay.
Excuse me?
Yeah.
What does it say after it? Is sharply
Concentrated.
concentrated. Okay.
Yeah, I thought you would ask, or somebody would ask this question. I pushed it. Yeah. See, because then we don't have to worry about the distribution or anything. We can just go through the expectation. Okay, so that's our plan. So this is now basic probability stuff we'll do first. So how are we going to use our concentration inequalities? So what are these? These are inequalities of the form in general. So you have some xn minus expectation of xn, some constant c1 times e to the minus n, some other constant c2 times epsilon squared, and usually epsilon is small. That's the form of the concentration inequalities. So let's do a little tour. So recall, this is sort of the minimum tool we need for theorems down the road. So recall Markov's inequality. So it says that for any non-negative random variable x and any possible t, the probability that x is greater than or equal to t is less than or equal to the expectation of x over t. Okay. So, well, so given this is a second year probability stuff, let's do this. So I'm breaking my, so that's the definition of expectation. I'm breaking into two parts, 0 to p and from t to infinity. So this is because it's non-negative random variable. And this is going to be strictly greater than or equal to the integral from t to infinity. Because I'm just dropping a piece that is non-negative. And this will be greater than or equal to t integral from t to infinity d f of x. Because I just pulled one constant out and let it be t forever. And that's just what we want. That is simply t times the probability of x greater than or equal to t. So let's just prove Markov's inequality. So now we'll use Markov inequality in a sort of sequence of inequalities we need. Okay, so now let S be some non-negative real number, then positive real number, then for any random variable x and any positive number t by Markov's inequality, we just saw probability of the random variable x greater than or equal to t is equal to the probability of e to the s x greater than or equal to e to the st. Okay, so I've done nothing. I just use sort of set of all omega, where x omega is greater than or equal to t. I have the same set. I'm just representing it through these exponential transformation, through the Sx transformation. So then this is just less than or equal to the expectation of e to the Sx over e to the st. Okay. So e to the st is like my right-hand side of the Markov inequality. So then there is this clever bounding method by Chernoff. So in Chernoff's bounding method, we find an s greater than 0 that minimizes the expectation of e to the Sx over e to the st, right? So the upper bound. So it's the idea, so if x1 to xn are IID x1, so they all have the same distribution, and Sn is defined to be the sum of the xi's, for S for the capital S for the sum. Yeah, so I should probably, this is, this is your lowercase s. So if Sn is just the sum of the xi's, then we get this. We get the probability that Sn minus expectation of Sn greater than or equal to t is less than or equal to e to the minus st expectation of ext s that goes from 1 to n of xi minus expectation of xi. And this is just e to the minus st product. Try the things. So what does this mean? Finding a tight bound, problem of finding a tight bound. Okay, so what we're using is that the problem of finding a tight bound is equivalent to finding a good upper bound for the moment generating function. So this problem is simply equivalent to good upper bounds or so what we've written there with e to the Sx and all that is called the moment generating function of xi minus expectation of xi. Okay, so this brings us to lemma 4. We will use this guy heavily downstairs. So upper bounding the moment generating function, upper bounded random variable. So is this okay? Let's just do all the inequalities that we need and prove everything so there's no ambiguity. So let x be the random variable with expectation of x equaling 0, and it's bounded above by a, b, and below by a. Okay. Then for s greater than 0, we have the expectation of e to the sx is less than or equal to e to the s squared times b minus a the whole square divided by 8. So that's a nice equality. So the proof is by convexity. So by convexity of e to the sx, what do we have here? So let's look at it as a function. A, B, and say x is somewhere here, and what we have is e to the sx, going to be like this, okay? And at this point and this point, we're going to interpolate like that. Oops. So that's basically the proof. So e to the sx is bounded from above by the line, which is x minus a over b minus a, which is the width, times e to the sb plus b minus x over b minus a times e to the sa. Okay, for x between a and b. Okay, so that's line is above e to the sx. And then since the expectation of x is 0, we have the expectation of e to the sx is less than or equal to the expectation of x. Now bring these random variables, a e to the sb plus b minus x divided by b minus a e to the sa, and this is simply minus a over b minus a e to the sb plus b over b minus a e to the sa. Okay. So this is going to be my, I'm going to call this guy my p. I'm going to call this guy my 1 minus p. So that is 1 minus p. So then this is going to be, that term is going to be equal to p e to the sb plus 1 minus p e to the sa, which is equal to p e to the sb over e to the sa plus 1 minus p e to the sa over e to the sa. So we'll multiply by e to the sa. And some more algebra. So this is 1 minus p plus p e to the sb minus a to the SA, which is 1 minus p plus p, e to the s b minus a, e to the minus b s b minus a. And this is my definition of e to the phi of u.
What is u?
Huh?
What is u?
Well, so where u is SB, just redefine. So can I push this up? Okay. And phi of u is equal to minus p u plus log 1 minus p plus p. Okay. Now you can just take the derivative, d by du of phi of u, and this is just minus p plus 1 over thing u, and then p to the u, and this is just minus p plus p over p plus 1 minus p e minus u. Okay, so then so thus phi of 0 is phi prime 0 0, and phi double prime of u is phi 1 minus p e to the minus u over p plus 1 minus p e to the minus u the whole square, which is less than a quarter. Okay. So why is that? Since p is strictly between 0 and 1, and e to the minus u is then strictly less than 1. Okay. So then we have our old Taylor's theorem. For some t in 0 to u, we have the following equalities. Phi of u is phi of 0 plus u times phi prime of 0 plus u square over 2 phi double prime of c, and this is going to be less than or equal to u square over 8, which would be s squared b minus a the whole square divided by 8. And that proves our theorem. So if things are bounded, we have this bounded difference inequality. That's our lemma 4. So the next theorem, so next one is called theorem 5, and it's Hofting's inequality. How are you guys doing? I'm not looking good. Too fine. It's okay? I know it's kind of mechanical, but I thought, I don't know. I think it's Nussbaum. I think like German comes with it. I really like to go through everything. So Hofting's inequality. Okay, so let x1, x2 up to xn be independent random variables. such that so usually Huffington's inequality you see in, I don't know, you see it in advanced undergrad or grad level?
Depends a bit on the teacher.
Okay. Yeah.
How fond they are of concentration inequalities.
Yeah. So let's say maybe independent random variable such that xi is bounded in this interval ai bi. So each xi has its own upper bound and lower bound, probability 1. Then for any t positive, the probability that the sum of the xi, so capital Sn is still the sum of the xi's, expectation of Sn being more than or equal to t is less than or equal to e to the minus 2t squared divided by the summation as I goes from 1 to n bi minus ai the whole square. And the other way also is fine. The probability that Sn minus expectation Sn being less than or equal to minus t is less than or equal to e to the minus 2t squared divided by summation side goes from 1 to n of bi minus ai whole squared. Okay, that's Huffington's inequality. So how do we prove it? So we're going to use the Chernov's bounding method. Okay. So we just saw for any positive s, little s, and t, we have following. I'm going to move to the next board. So we have the probability that Sn minus expectation of Sn more than or equal to t is less than or equal to e to the minus st times the product as I goes from 1 to n of s xi minus expectation of xi. So this is less than or equal to e to the minus st times the product 1 to n e to the s squared bi minus ai whole squared over 8. This is just applying this. Now what is this from? By lemma 4. Since each of the xi's are less bounded between ai and bi. So we just apply lemma 4 over and over, and because the expectation of xi minus expectation of psi is 0. So this is just e to the minus 2t squared divided by summation as I goes from 1 to n of vi minus ai the whole squared. How do we get that? By choosing s to be, the small s, to be the argmin of minus st plus s squared squared divided by 8. Okay, and if you look at the argument here, this will be 4t divided by this sum. Okay. And that's what we basically put in here. Okay, so similarly you can show for the probability Sn minus expectation of Sn less than or equal to minus t. This is simply the probability expectation of Sn minus Sn is more than or equal to t. And okay, so this familiar example people may recall is when xi's are Bernoulli. Right? So example, if x1 to xn are IID Bernoulli, these are the variables, then this inequality becomes the following: probability of Sn over n minus b being more than or equal to epsilon is less than or equal to e to the minus 2n epsilon squared. So it's the same inequality, we just divide everything by n and things cancel here, but and we use the fact that Bernoulli is between 0 and 1. Okay, so now lemma 6 is expected maximal deviation inequality. I forgot how many there are in total. Huh? This is the minimum, okay? Okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 inequalities conspire for this final result. No, there's way more than 9 inequalities. But yeah.
This is a stronger statement than this old quote by Kolmogorov, where behind every good result there's an inequality. Behind this result there are 9 inequalities. Yeah. So just imagine how good this result must be.
I know. Yeah, and they're all necessary too, so they're not like redundant. Yeah. So,
only analysts throw in some extra inequalities just for fun.
Oh, really? Well, you're publicly talking about analysts, so I don't know. I don't know, man. I don't call myself anything. I'm a human being trying to make a living, doing whatever I can. So, I'll do some analysis.
I think if this is all you do, then you're in the wrong business, right? Because
yeah,
you can do this much more easily enough.
Yeah, I don't know. I just find the whole. Actually, academia, like anywhere, like even in biology where I used to work, like I find this whole tribal culture like completely. I don't like it. So I think in some sense it's always good to start your own company. It's your own tribe, but at least there's no war inside, maybe.
What does this have to do with concentration inequality?
Well, he's just talking about styles of mathematics. I think it's healthy to have tribalism in academia. It's a natural reaction, so then people push the frontiers in different directions, which is good for human knowledge. So anyway, let's get back to concentration inequality. Or mass concentrations. So this is lemma 6. So this one is, so there's actually an interesting social psychology study done about academics. It isn't Science or Nature or something. So they actually went into this in detail. And apparently maths is like the most civil, because people are like kind of can argue with each other formally. And apparently, like in other disciplines, it can get really trench warfare. And there's this article that goes into this in detail. People, behavioralists, psychologists don't like personalities. Like, I don't know, they're quite serious. Okay, expected maximal deviation inequality. So now let sigma be greater than 0, n be greater or equal to 2, and let y1 through yn be real valued random variables. Such that for all little s greater than 0 and every I between 1 and n, the expectation of e to the s yi is less than or equal to e to the s square sigma square over 2. Okay. So if this is satisfied, then the expectation of the maximum over all I, all yi, is less than or equal to sigma times the square root of 2 times the natural logarithm of n. And additionally, the expectation of e to the s times minus yi is less than or equal to e to the s square sigma square over 2 for every s more than 0, and for all I between 1 and n, then for any n greater than or equal to 1, we have this, we have the expectation of the maximum of the absolute value of yi is less than or equal to sigma times square root of 2 ln of 2. So that's the expected maximal deviation inequality. So the proof. So let's recall Jensen's inequality. So what is this? Basically, if G is convex, then expectation of G of x is greater than or equal to G of expectation of x. And if G is concave, then the expectation of G of x is less than or equal to G of expectation of x. Okay. Yeah.